Welcome back for this second lecture of this mini course, and the next goal for us is gonna be investigate the method the strategy for the proof by Chen and Chen. Okay. Actually, the method is gonna be illustrated much more in detail by Professor Pingali, because the Calabi conjecture actually is proved through the same method, and I believe Professor Pingali will spend part of this lecture, of his lectures, on explaining the continuity method. So for us, we just make some comments here. So continuity method for the Calabi conjecture will be applied to a second order elliptic PDE. In this case, we are facing a fourth order elliptic PDE. Actually, continuity method can work for, has no actually requirements on the order or the structure of the equation PDE to solve. The ingredients we need are a continuity path in this case. Continuity path was proposed in 2015 by Professor Chen Shuzhong, and the path is T times the difference between the scalar curvature of Kähler potential phi minus the average on the Kähler class of the scalar curvature equals to 1 minus T times trace according to phi of omega minus n, where trace is, just to recall it, is omega phi n minus 1 wedge omega over omega phi to n. What should we remark about this continuity path? For instance, that it is the Euler-Lagrange equation of the functional T K phi. This is because we saw earlier that the critical points of the K energy are precisely this constant scalar curvature Kähler matrix minus 1 minus T, and this again from the previous lecture we saw this comes from the J functional. So this is gonna be the J functional of omega applied to phi. Okay. I think we do not label particularly this function here, but we give it a name. It is the twisted K functional, K energy actually. And this is, we can say, this is the twisted component. Okay. Let me see if I get the signs right. Actually, this should be plus here. There was a sign issue. Okay. Another thing we can say about this continuity path is that for t equals 0, any continuity path should have at least the value of the parameter of the path for which the equation becomes easy to solve, or at least has a solution. It becomes trace omega minus 0, which has solution phi equal to any constant in the Kähler class, or phi equal to 0 in the normalized Kähler class. Okay. So the second ingredient here for the continuity method to run is the openness part. Okay. And so we can see from here that the trace according to phi of omega is of second order. So this part is second order, and here we have 4 derivatives of phi, so this is a fourth order part. Okay, then there is a jump of order of this equation. For t equal to 0 is the of second order, and then for any other t it becomes of fourth order. So this is one peculiarity, jump of order of the PD and so this jump is quite an issue, and we can see the interesting thing is to prove the delicate point is to prove the openness at this jump. Okay, so then we notice that the openness part was solved by Chen-Shu for t greater than 0, And then first proof for the jump, in the jump situation, was given by his student Song Yu, PhD thesis. For any t. Of course, the parameter here runs between 0 and 1. And for t equal to 1, we have the equation we want to solve. Then, okay, then about Zongyu's proof, the ingredient used here is a quantitative version of inverse function theorem. Okay. Now, with this result on the easy solution plus the openness, putting together these two things, we can say that as consequence, the equation has a solution for t in some interval from 0 to some epsilon, where epsilon is positive and depends on the initial data. Okay. Then from now on, we consider the continuity path for t in say epsilon to 1. And this epsilon comes directly from the data and is a positive number. Okay. The part which is more important for us is the focus of this series of lectures is actually the closedness part. On its turn, this can be divided into two parts. Part A, which is if K is proper, according to the definition given in the previous lecture, then the supremum for T belonging to epsilon 1 of the entropy of phi t is finite for any phi t C for alpha solution of the path. And part 2 are the a priori estimates. Depending, so up to order C for alpha, depending on the entropy of phi t. So from part A, using the hypothesis of properness, we can derive the bound on the entropy, and this bound on the entropy can now be one of the variables of these a priori estimates. Okay, let's just say something about the part A, and next lectures we are gonna investigate in details what is the core of this series of lectures. So part A, it goes as okay. Part A, step 1. So step A1 is actually we give a reference for this is corollary 4.5 in the second paper of the series. For any T0 in epsilon 1, given phi T0 solution of the path at T0, then T0 K phi T0 plus 1 minus T0 J omega phi T0 is equal to the minimum of the potential in the Kähler class unnormalized T0 K phi 1 minus T0 J. So to describe this result, we can say that a solution of the continuity path is a minimizer of the twisted K energy. And to get this result, Chen and Chen they make an application of They build on results by Berman, Darvash, Lu, Berman and Benson, and also the theory of Chen Shushon on geodesics of the Kähler class. Okay, then step A2. From step A1 we have for any T0 between epsilon and 1, we have T0K by T0 plus 1 minus T0 J omega phi T0 is less or equal than phi T K for the zero potential, so for the reference metric, plus 1 minus T0 J omega at 0. This can also be seen as with a direct computation, and this linear combination is bounded above by the maximum between the K energy at 0 and the J omega functional at 0. Now, I'm sorry. From step 1, we see that since this is a minimum at any point, this is bigger. Okay, so we choose the point phi equal to 0. Why we choose this? Because in the next step we use that, and this is actually the direct computation, J omega is minimized at phi equal to 0. Then a twisted K energy at phi T0 is sorry, this guy over here, where this is 0, is less than the K energy at phi T0, okay, which we saw before is bounded by the maximum between K at 0 and J omega at 0, okay? Okay, then we have the following. K phi T0 is bounded by 1 over epsilon of the maximum between K0 and j omega 0, which we saw is 0. Okay? Now, properness says that if a sequence of Kähler potential has distance from the origin which goes to infinity, then also its k energy goes to infinity. Here we can regard the T0 as a parameter of the sequence. The k energy is bounded then by properness for any t in epsilon 1. The distance d1 from the origin to phi t is bounded. Okay, or t0 or t0. Okay? Now we go to step 5. And step A5 uses peculiarities of the D1 distance by Tamas-Darvas. Okay, so there exists a constant depending only on n and omega, such that for every potential normalized, then j of k of phi absolute value is bounded by c times maximum over m of k omega d1 0 phi. So the conclusion is, remember we want to find a bound on the entropy. The supremum for T0 between epsilon and 1 of the entropy of phi T0 is less than the supremum of the entropy 0 plus j minus Ricci of the background metric in PT0 plus supremum in the same interval of the absolute value of j minus Ricci PT0. Entropy plus j functional of minus Ricci is precisely the k energy. And for this we have the formula by Darvas, and so this can be bound by c times maximum over the manifold of Ricci background norm with respect to the background metric times the supremum T0 in epsilon 1 of the V1 distance from 0 to phi T0. And this supremum is bounded because of the step A4. Also, the K energy, as we saw again in step A4, is bounded. So this term is bounded, this is bounded also. We have the bound for the entropy as wanted. Okay, next goal for us will be to investigate finally the a priori estimates, and that's all for now. I'm over time, I'm sorry, and we'll resume after break.